All right, chem students, here is a small review for the acid-base quiz that's coming up. So there are a couple items that you'll want to cover, and they're here under what success looks like. So I'm just going to go over each one with examples. So the first one is converting pH and POH to hydrogen and hydroxide concentration. So here's an example. If you have a solution that is 8.35 pH, then what are the concentrations of hydrogen and hydroxide, and then what's the POH? So if you take the pH and you raise it, do 10 to the negative pH, it will give you the concentration of hydrogen ions. And so I did it here. And then you're given a very small value. And remember, this is in molar. So this is back to a previous lesson, but molarity is moles, number of moles per liter. So, and you should remember what moles are. It's a unit of measurement that we use in chemistry. So then once you have that, the next logical step is to take 14, which is the highest number you can get for pH or POH, and you subtract the pH from it, and that would give you the POH, because pH plus POH equals 14. So then 14 minus 8.35 gives you 5.65, and that is going to be the POH. And then again, you do 10 to the negative POH, just like you did for the pH. That'll give you the concentration of hydroxide, and you have your value here. And I forgot to put the M for molar. So again, concentrations, if it's in brackets, it needs the units molar. If it's a pH or POH, it's just a value or a number. The next one is identifying Arrhenius acids and bases, Bronsted-Lowry acids and bases, and Lewis acids and bases. And I like this diagram. I pulled it off of Quizlet. And I like it because it demonstrates which one encompasses which. So the most restrictive definition is going to be Arrhenius, and the least restrictive or most encompassing is going to be the Lewis right here. So starting with the most encompassing, so Lewis dot structures, which we've done before. The acid is going to be the one that accepts the electron pair, and the base is going to be the electron pair donor. The Bronsted-Lowry, a little bit more direct in that the acid is going to be the H plus donor, and the base is going to be the H plus acceptor. And this is why usually hydrochloric acid has an H in front, and when it reacts, it loses that first H. And then for the base, something like sodium hydroxide, which we'll see later, it loses the Na and becomes OH negative, and it's able to accept the H plus. Then the last one is going to be the Arrhenius, and this has to do with acids donating H plus and bases donating OH negative. And there is some reading in the homework that goes over this and gives even more examples than I provided here. The next one is determining the equilibrium for acids and bases. I'm only going to show an example of the equilibrium for acids, but it's the very same process for bases. So here's the formula up here, so you can kind of see it here. Ka equals, and then on the top you put the concentration of, and just similar to the Keq, which is the equilibrium constant, you put the products on top. So H plus and A negative, so A refers to the acid part, and then the actual acid before it disassociates is HA. So here's an example. Hypochlorous acid, which is HClO, is a weak acid. So weak means that it's not going to disassociate very well, which I'll talk about in a little bit, which means that the Ka should be very small. So that's what you should think is weak means that the Ka is small. If the Ka is very large, then it's going to be a strong acid. So it tells us that to determine the Ka, if the concentration of the solution to start with is 0.25. So, and it has a pH of 4.07. So you write the chemical equation first, so HClO, and you have to remember how it disassociates. So it's going to break into H plus. Since it's an acid, this H plus is here, and then the ClO negative is there. And then moving on, you then write down what you know. So you know that the concentration of HClO before you start the reaction is 0.25 molar, but this is before, and we need it at equilibrium or after. So therefore, we have to take the 0.25 and we have to subtract an amount. I already did this, but I'll explain where this value comes from. So we are given that the pH is 4.07. So from there, we can determine the concentration of H+, which is part of the equation up there, right here. So 10 to the negative 4.07 gives us 8.5 times 10 to the negative 5 if you do it in your calculator. So therefore, in order to get this amount, we have to subtract it from the original acid concentration because it is an equilibrium reaction. So if you start with this amount here and you take some of it away, it has to pull it from here over to here. And so this is kind of like making one of those ICE tables, initial, change, and then equilibrium. So 0.25 minus 8.5 times 10 to the negative 5 gives us a ending concentration of 0.2499 molar for the acid. Then the H plus concentration is here. And then from the equation, we know that it's a 1-to-1 ratio between H plus and ClO negative. So therefore, the concentration should be the same because they will dissociate into the same amount. So 8.5 times 10 to the negative 5 molar for the H plus, and the ClO negative is 8.5 times 10 to the negative 5. The unknown, so that's the Ka. So I just plug values in. So here's the formula. You have your H plus and your ClO negative right here, just like the equation right here. Those are my products. Those go on top. And then on the bottom, I put my acid concentration. I plug it in, solve, and we notice that it is less than 1, really less than 1. It's 10 to the negative 8. It's really, really small. So therefore, it proves that it's a weak acid, or it's not really going to go to the right very well. So that leads us to, well, here's the example of the equilibrium constant for bases. You would do a very similar thing. But that leads us to a discussion or a picture of weak acids and weak bases. So a strong acid like hydrochloric acid, the only difference between that and a weak acid, like carbonic acid right here, is that HCl dissociates very well, which means that H and Cl will separate almost every time. But when you have a weak acid, only some of them separate and some of them stay in solution as the acid before dissociation. So you can see that in the diagram here. Some of the green circles represent the acid that has not dissociated, which means it is weak. But the strong one here means that you have a lot more H plus for the same amount. So that's something to note, is that if I have the same volume, so I put, let's say, 10 milliliters here and 10 milliliters here of two different acids, if I put 10 milliliters of HCl, I'm going to get a lot more H pluses in the solution than I am if I put the same amount of H2CO3 or carbonic acid. I will get less H pluses because it's not breaking apart as easily. And that brings us to the last one, which is given an experiment, and this is for application, so this is a requirement. Determine the starting molarity of a substance. So what is the pH and concentration of the hydrogen and hydroxide ions once the acid base is neutralized? That's a good question to ask yourself. So you have a student who's trying to neutralize an acid, so maybe they have an upset stomach and they need to take Tums by using some sort of base. Tums is a base. Seeing as their little sibling has ripped the instructions off the package, they now must determine how much they have to take. So, being a good chem student, they set up an experiment. How about that? So they measured 25 milliliters of the unknown acid. So that's going to represent their stomach acid. And they put it in a clean flask. So they put it there. Then they take a device that can drop small amounts of base into there. And the base, we know, is 0.5 molar because they were able to prepare it. So that would be like the Tums. So they're going to drop one drop at a time. And we did an experiment like this online, a virtual one, that was very similar. Once the color changed, and that's what it says here, the NaOH has an indicator that turns pink when the solution is neutralized. Stomach relief, right? So then the student adds drop by drop, determines that it takes 15.4 milliliters of 0.5 molar NaOH to reach equilibrium, which is the pink color, which is a neutral pH, a pH of 7. So with a pH of 7, we can now proceed forward, and that is take the information that you gained from the experiment and determine what the concentrations are of everything. So here's what we know. We know that we can write a chemical formula for this reaction. We know that we have hydrochloric acid here, and we have NaOH here. We can write it like this. HCl, aqueous, again, this is all taking place in water, and then NaOH. Those two combine and you always get a salt, and you get water. But here I made a note that usually it just produces water if it's neutral. But if it's not neutral, and you have more of one than the other, so if you have leftover acid, then you'll have leftover H pluses. But if you have leftover base, then you'll have a lot of OHs in the solution, which means that a pH meter or some sort of color indicator will change color. So a neutral pH tells us that the H plus and the OH negative, so the hydrogen and hydroxide ions, they equal in concentration and in value. So if I do a little math, I can determine how many moles of NaOH that I had. So I had 15.4 milliliters, but I need to convert that to liters. We always deal with liters of NaOH. And if I multiply that by the molarity, moles per liter, the liters cancel. So this liter cancels with that liter. And so I'm left with moles of NaOH. So the amount of moles that I needed to use was 0.0077 moles of sodium hydroxide in order to neutralize 25 milliliters of the HCl. So then the question is, well, how much HCl did I need and what was the concentration? Well, here's how you solve this. And this is where you have to use previous information along with the new information about acids and bases in order to put those two together and use some problem solving skills. So the chemical equation states a couple things, that 1 mole of NaOH neutralizes 1 mole of HCl. So 1 mole of hydrochloric acid neutralizes 1 mole of sodium hydroxide. And so therefore, if I take my 0.025 starting of HCl and I multiply it by my unknown molarity, which is what I'm trying to find out, that's going to equal my moles of HCl. Well, according to the equation, 1 mole of HCl equals 1 mole of sodium hydroxide. So if I have 0.0077 moles of sodium hydroxide, which I have up here, I solved for it, then I would have the same amount of HCl. So then it becomes just an algebra problem. I set this equal to these two, and then I solve it. So then I multiply both sides by 0.025, which I've done here, right? Or sorry, I divide it. Since it's multiplication, I divide by 0.025. And then I get a concentration of 0.308 molar HCl. So if you have any questions, please email me. Feel free to. I'm going to open the test tomorrow, but I will give you all the way until the end of the day on Tuesday when we get back from or end of the day on Wednesday, when we get back from our break. All right.